This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on applications of exponential functions. Our first one is continuous compound interest. So our formula is A equals PE to the RT. A is the amount of money in the account, P is the principal, the initial investment, R is the annual interest rate, and T is the time in years that the money is invested. So keeping all this in mind, let's answer the following question. $5,000 is invested in an account paying 2%, compounded continuously. How much is in the account after 4 years? So we have A equals PE to the RT. P is our initial investment. P is 5,000. 2% continuously. That's 2% per year continuously. That's the R. R will be 0.02. After 4 years, T will be 4. So 5,000 E to the 0.02 times 4. Now, you certainly cannot do this without a calculator, so that'd be the best you could do. With a calculator, you're going to get 5,000 times e to the 0.08, or about 541644. Next up, we're going to ask how much time must pass before the original investment doubles. So our original investment is 5,000, and we're going to double it to get to 10,000. Or you could just think of it as p to 2p. Either way would work. I've got 5,000 to 10,000, and then when we divide both sides by 5,000, of course, we just have 2 equals e to the 0.02t. To solve for t, we're going to have to take the natural logarithm of both sides. So natural log 2 equals natural log e to the 0.02t. 0.02t can come down in front, so log 2 is 0.02t times the natural log of e. Natural log of e is 1. So we get natural log 2 is 0.02t, divide by 0.02, and we get t is log 2 divided by 0.02, which is the best you could do without a calculator. With a calculator, you can get approximately 34.7 years, is how long it would take for the original investment to double in that case. Our next model is an exponential growth and decay model. So the number we have is the initial number times e to the kt. N of t, the number or amount present after t years. N sub 0 is the initial amount or number present. K is our growth decay constant. If k is positive, N is growing, it's increasing. If k is negative, it's decreasing or decaying. T is the time that we're going to use depending on the context. So here we're using a problem with a radioactive isotope. And we're saying it has a half-life of 100 years. That means when 100 years passes, half is present. So we're going to solve for the growth decay constant. The amount of isotope should be decreasing, hence we're expecting it to be decay. We're expecting k to be a negative number. So we're starting with our initial amount, n sub 0, and then we're going to have half as much of it, n sub 0 divided by 2, and when t equals 100 years. So dividing both sides by n sub 0, we're going to get a half equals e to the k times 100. If you wanted to, you could have maybe put 1,000 for n sub 0 and 500 for n of t. That also would have worked. You would have still gotten 1/2. To solve for k, we're going to need to take the natural log of both sides. So natural log of 1/2 equals natural log e to the k times 100. The k times 100 is going to come down again using our property of logarithms. So natural log of 1/2 is k times 100 coming down times the natural log of e. Natural log of e is 1. Natural log of 1/2 is 1 times 100 times k. To solve for k, we'll divide both sides by 100. And we have k is log 1/2 over 100. Except you can make this a little simpler because you could use your property of logarithms to recognize that the log of 1/2, the log of the quotient, is the difference of the logs. You could say k is log 1 minus log 2 over 100. And you could remember that the natural log of 1 is 0. E to the 0 is 1, so that would just become 0 minus log 2 over 100. So to make it a little cleaner, we can get our growth constant, k, is negative log 2 over 100, which is a negative number, as we expected, because the radioactive isotope is decaying. If our total number is decreasing over time, our k has to be negative. If you have a calculator, you can approximate that to negative 0.00693. We're going to continue with this exponential growth and decay model. This time we're going to look at growth. It says a population of insects follows an exponential growth model, at least in the short term. At first there are 500 insects. 2 days later there are 2,000 insects present. They're growing pretty fast. How many insects are present 6 days from the start? So here is our formula. The number of insects we have is the initial number times e to the kt. So at first there are 500 insects. So n sub 0 should be 500. 2 days later, t is 2. T is represented in days in this problem. 2,000, the n of t would be 2,000. And then we can use that to solve for k. So again, n of 0 is 500, t is 2 days, n of 2 is 2,000. Plugging all that in, we get this. Dividing by 500, 2,000 divided by 500 is 4. And we get 4 equals e to the 2k. Next up, to solve for k, we're going to take the natural logarithm of both sides and see what we get. Natural log 4 equals natural log e to the 2k. 2k comes down front, so natural log 4 will equal 2k natural log e. But we know natural log e is 1, so we have log 4 is 2k, and then divide both sides by 2, and we get k is log 4 over 2. But actually, we can do a little more with this if we want. Let's continue. So k is log 4 divided by 2, which we could rewrite as 1/2 times log 4. Then we could pull the exponent up to say that that's log 4 to the 1/2 power. But what does that mean? 1/2 power, of course, is square root. That would be the natural log of the square root of 4 is k. And we can simplify that to give me log 2 equals k. And that will actually make using that a little bit easier for us. So our goal is to get how many insects are present 6 days from the start, or n of 6. So this is the stuff we're given, and we've just found out that k is log 2. We want to know what n of 6 is. So my initial term is 500 e to the k. We simplified k to be log 2 times 6. But now e and natural log are inverse operations, so e to the log 2 is just 2. And e to the log 2 times 6 is just 2 to the 6th. And we get n of 6 is 500 times 2 to the 6th power. 2 to the 6th, 2, 4, 8, 16, 32, 64 times 500, and we get 32,000. So 6 days from the start, we have 32,000 insects, assuming that this population model holds. But the problem with this population model is it grows forever. And eventually you're going to get to a point where you can have no more insects. And that's when the logistic model comes into play. So here's how this works. A certain species is measured by this population, which is a little more realistic for environments that are constrained. So some number on the top, 1 plus some number e to something t. That is in essence how our logistic model is going to work. So let's do some analysis with this. The first question asks how many individuals are initially present. That would mean when t equals 0, what is the population? What is p of 0? So plugging in 0, I will get on the bottom 1 plus 199 e to the negative 0.3 times 0. Now negative 0.3 times 0 is 0. E to the 0 is what we're going to get down there. But what is e to the 0? E to the 0 is, of course, 1. So it's just 2,000 over 1 plus 199, or 2,000 over 200. And that's easy to divide. That, of course, just gives us 10. So initially we have 10 individuals present in this population. Next up, we want to see what happens as t goes to infinity. So we have this 2,000 over 1 plus 199 e to the negative 0.3 t. As t goes to infinity, how is p of t changing? Well, I start with this part, e to the negative 0.3 t. If you have a negative exponent, it's in the denominator, so it might be easier to think of it as 1 over e to the 0.3 t. Now, if t gets very large, a million, a billion, a trillion, I have e to a large number. E to a large number is a really large number. 1 over a really large number is going to get closer and closer to 0. So that's going to go to 0 as t goes to infinity. Then the question is, what does this whole thing do? So as t goes to infinity, p of t will go to what? We know this piece goes to 0. So it'll be 2,000 over 1 plus 199 times 0. Well, that of course just gives me 0. I'll have 2,000 over 1, which is 2,000. So we're starting out with only 10 members of this species, 10 individuals at time 0. But as it goes to infinity, the number of individuals should get closer and closer to 2,000. 2,000 will be the long-term number of elements in this population. Okay, our next question is, what is the population 10 years from the initial time? That's going to require us to plug a 10 in for t. That'll be negative 0.3 times 10. Negative 0.3 times 10 is just negative 3. So we get 2,000 over 1 plus 199 e to the negative 3, which if you had no calculator, as far as you could go. But with a calculator, you can see that that's approximately 183 individuals. So we grow from 10 to 183 in 10 years. And as we get closer and closer to infinity, we know it will grow to approximately 2,000. Our next question is, how many years must pass before the population is 2,000? Check that, it's 500. So if p is 500, what does t have to be? So 500 over here, solve for t. How are we going to do that? Well, we're going to multiply both sides by this denominator, 1 plus 199 e to the negative 0.3t is going to get here. And then you'll notice that these cancel, and I get 500 times 1 plus 199 e to the negative 0.3t equals 2,000. You may be tempted to distribute, but don't. It would be simpler to just divide both sides by 5,000. So if I divide the left side by 5,000 and the right side by 5,000, I would just have 4 on the right side. And that's going to be easier for us to work with. And our goal again here is to solve for t. So let's see how we're going to do that. We're going to wind up subtracting 1 from both sides. So 4 minus 1 is 3. And we get 199 e to the negative 0.3t equals 3. Our goal is to solve for t to find the number of years. Divide both sides by 199. So we get e to the negative 0.3t is 3 over 199. Next up, take the natural logarithm of both sides. This exponent can come down front. Negative 0.3t log e could equal log 3 over 199, which we could use the fact that the log of the quotient is the difference of the logs. So first off, pulling the exponent down, negative 0.03t natural log e equals log 3 over 199. Natural log e is 1. And on the right side, natural log 3 over 199, I decided to rewrite it as log 3 minus log 199. The log of the quotient is the difference of the logs. And all we have to do now is divide both sides by this coefficient on t, negative 0.03. Divide both sides by negative 0.03, and we get t is that value. Which again, without a calculator, is as far as you can go. If you have a calculator, you can get your approximate value of about 140 years. So it's going to take quite a while to get to 500 elements. And that will conclude this lesson.